You know, when we first learn about circuits, everything is perfect, right? The wires have no resistance, the batteries are ideal voltage sources, but as we know, the real world is a whole lot messier. And it's in that mess, in those so-called imperfections, where the truly interesting physics happens. Today, we're going to bridge that gap from the ideal textbook circuit to how things actually work.
And to guide us, we're going to solve a puzzle that I'm sure you've all experienced. You're standing in your kitchen, the refrigerator suddenly kicks on with a hum, and for just a second, the lights dim. Why? What is actually happening there? It's a perfect, everyday example of the physics we're about to unpack. And by the end of this, you'll be able to explain it precisely.
All right, to get to the bottom of our refrigerator problem, we have to start at the source, the very heart of the circuit. And in our perfect ideal world, we describe that source with one core concept: electromotive force.
Okay, let's get something straight right away. Electromotive force, or EMF, is kind of a terrible name. It's a leftover from when scientists like Volta were first figuring this stuff out. It is not a force. It's the work done per unit of charge, joules per coulomb, which, of course, is a volt. So you can think of it as the ideal voltage of a source, its absolute maximum potential difference when nothing is connected and no current is flowing.
So how does a source, like a battery, actually create and maintain this voltage? Well, it acts like a charge pump. Inside a car battery, for example, you have chemical reactions that provide the energy to do work on charges. They literally grab charge carriers and move them from the low potential terminal to the high potential terminal, fighting against the electric field the whole way. It's this constant separation of charge that maintains the EMF ready to drive a current. So that's the ideal model, nice and clean. But of course, the real world is never that simple. The very stuff that makes up our charge pump, the chemicals, the electrodes, gets in the way. It's time to introduce our first and most important dose of reality: internal resistance. An ideal battery is just a pure EMF. Its terminal voltage would be the same no matter how much current you pull from it. But a real battery is made of actual stuff: electrolytes, metal plates, and that stuff resists the flow of charge. We lump all of that together and call it the internal resistance, R. And the second you start drawing current, this resistance starts to matter a lot. This is such a great way to visualize what's happening. We model a real battery as a perfect EMF source, epsilon, right next to, in series with, a small internal resistor, R. The graph on the right really shows you the journey of a charge. The chemical reaction pumps it up to the full potential of the EMF, but then before it can even leave the battery, it loses some of that potential, crossing that internal resistance. That drop is a classic Ohm's law drop, I times R. And all of this brings us to a really fundamental equation. The terminal voltage, that's the actual measurable voltage between the battery's posts, is the ideal EMF, epsilon, minus that internal voltage drop, IR. So what does this really mean? It means the more current you draw, the bigger IR gets, and the lower your terminal voltage becomes. A battery under a heavy load is just not as good at providing voltage. Okay, so now that we have a much more realistic model for our power source, let's start building up the tools we need to analyze the rest of the circuit. And we'll start with the simplest arrangement you can have: resistors in series. When we talk about series, it's all about one thing: the path. The current flows through the first resistor, and it has absolutely nowhere else to go but straight into the next one and then the next one. It's a one-lane road for the charge. And this single-path setup has some really key consequences. First, because charge is conserved, the current has to be the same through every single resistor in the chain. It can't just disappear. Second, because energy is conserved, the total voltage from the source gets divided up among the resistors. Each one takes a piece of the total potential drop. And finally, putting it all together, the total equivalent resistance is just a simple sum. You just add them up. Easy enough.
All right, that's series. Now let's flip the script and look at the other fundamental configuration: parallel circuits. And here, the rules are completely different. So what makes this circuit parallel? It's all about how it's wired. You have a junction, or a node, where the main current arrives. Then it splits, giving the charge multiple paths to take. All the components are connected across the very same 2 points in the circuit.
So what are the rules here? Well, first, since every resistor is connected between the same 2 points, the voltage drop across each one has to be identical. Second, that current that arrives at the junction has to split up. The total current going in must equal the sum of the currents going out through each branch. And finally, the equivalent resistance, well, it's this reciprocal formula. And this is a super important takeaway. Adding more resistors in parallel actually lowers the total resistance because you're opening up more lanes for the traffic of charge to flow.
Okay, great. We've got series and we've got parallel. But let's be real. Most circuits you'll actually encounter are a mix of both. So let's put it all together and figure out how to tackle a more complex, more realistic network.
All right, when you see a circuit like this, the key is not to panic. You just break it down piece by piece, looking for simple patterns. The first thing that should jump out is that R3 and R4 are clearly in series. The current goes through one, then has to go through the other. So we can just replace them both with a single equivalent resistor. 6 plus 4 gives us 10 ohms.
See how that cleaned things up? Now a new pattern is obvious. Our new 10-ohm resistor is sitting in parallel with R2. They're both connected across the same 2 points, so we use our parallel formula. 1 over 10 plus 1 over 10. That's 2 over 10. We take the reciprocal, and we get 5 ohms for that whole section.
And just like that, we're on the home stretch. What's left is a simple series circuit. We've got R1 in series with that 5-ohm block we just calculated. So we do one last addition, 7 plus 5 gives us a total equivalent resistance for the entire network of 12 ohms.
And here's the really cool part. After all that work, what we found is that from the battery's point of view, that whole complicated mess is exactly the same as one single 12-ohm resistor. So now calculating the total current is trivial. It's just Ohm's law. 24 volts divided by 12 ohms gives us a total current of 2 amps flowing out of the source.
Okay, deep breath. We've covered EMF, internal resistance, series and parallel analysis. We have all the tools. It's time to go back to the kitchen and finally solve this puzzle.
Okay, so here's exactly what's happening. Think of the wiring in your house walls as a small resistor, R1, in series with everything else. The light bulb, R2, and the fridge's motor, R3, are connected in parallel to that wiring. Now, when a big motor like that first starts up, its resistance is extremely low for a moment. Low resistance means it tries to draw a huge current. All of that current has to flow through the house wiring, R1. And what happens when a large current flows through a resistor? You get a large IR voltage drop. This drop in the wiring means the terminal voltage available for the parallel branch with the light bulb suddenly decreases. And since the power of the bulb, its brightness, goes as voltage squared, even a small dip in voltage causes a very noticeable dimming.
And you know, the beautiful thing is that this all ties back to one of the most fundamental principles in physics, conservation of energy. In any of these circuits, the total power that the EMF source provides has to be perfectly balanced by the total power being dissipated by all the resistors, whether that's as heat in the wiring or light from the bulb. It's a great way to double-check your work. If the power in doesn't equal the power out, you've made a mistake somewhere.
So, what we've really learned today is that the flaws in our components, the internal resistance of a battery, the tiny resistance of a wire, they're not just annoying details to ignore. They are absolutely critical to understanding why real-world circuits behave the way they do. Which leaves me with a final question for you. What other imperfections in capacitors or inductors or transistors are we often taught to ignore, but in reality are essential to how all of our modern electronics actually function?